Good afternoon. Thank you, Emil, for introduction. So my talk is going to be a bit more connected to technology, as I'm a researcher, and even though I will still try to stick to more general terms, and in essence, I will just try to give some quite broad introduction about what is biomechanics, what it actually can be used for, and how can we actually measure it. And then I will share some experience about the projects we are going to do with biomechanics in the Institute of Electronic and Computer Science, and in the end give some conclusions and suggestions for discussion. So in essence, biomechanics is a study where we're trying to study biological systems with the methods from mechanics. And for this talk, we're going to stick with human body and just with mechanics in terms of movements and postures and body part alignment of human body. So there are quite a broad fields where we could benefit from such information. I have highlighted just 3, but I'm sure you can find a lot more. So it's sports, human-computer interfaces, and also medicine, but as I said, there are much more fields as well. But just to give some examples, so for example, the most obvious application would be in sports, where we would be interested in order to measure the performance of athletes, the performance of their bodies, in order to fit them into some kind of model so we could benefit from more advanced training. And the same could apply to more or less any sport. For example, alpine skiing, we might be interested to see how the body is working when we're going down slope, and then just to compare it with some gold standard in order to give better advice for our athletes. But in addition, it doesn't have to be like high performance athletes only. Also, amateur athletes might benefit from additional monitoring and suggestions in order to provide a smoother training experience and then avoid unnecessary injuries. The other thing that I mentioned was human-computer interface. So here you can see just a bunch of people messing around with a Kinect sensor, but the idea is that they are controlling these animations with their body movements, and it could be any other application like high-performance gaming or whatever. And actually it could be also something more you could say serious or useful in practical terms. For example, here you can see an example where the tracking of finger movements is used in order to interact with real virtual objects, and in order to make this interaction more natural and seamless. And as it turns out, even though this motion capture is quite, you could say it's quite hard to do that, but it turns out that to synthesize natural movement is even harder. So, for example, when oftentimes when you do some animation for movies or gaming, then you do this 3 steps where you capture the real motion of human, then you apply it to your 3D model, and then you do some rendering to make it more fitting in the environment. And the last part is the main topic for today. It's medicine. Here I just highlight a few applications, but basically there could be quite a number of them. For example, here on the left you can see a gait analysis application. So it can be used for rehabilitation after some injuries or some diseases that are connected to limited movement. As well as on the right you can see the application, for example, for posture monitoring, where we might be interested in detailed analysis of human posture. And what I want you to bear in mind that in most of these applications I just showed, we are actually quite often interested not only in biomechanic measurement in some controlled environment, but the most interesting applications, in my opinion, is when you want to use it in your daily environment, in your daily, while you're performing your daily activities. And when we are starting to talk about how we can measure that, then actually we can divide the approaches for measurement of biomechanics in two or more or less broad terms. One approach is when we use external equipment. So here, as you can see, we're using some specially equipped surroundings. So we place around a bunch of relevant sensors and try to estimate what's happening to the human body. The other approach is when we put the sensors on the body itself. And as you can see, then the first approach is good because you don't have to wear any equipment. And actually, the most precise systems are using this first approach, but the problem is we are basically restricted to laboratory environment. And on the other hand, the wearable sensors are the ones that we would like to use if we want to get the measurements done in whatever environment. But the problem is that we have to carry all the electronics we need on us, which often is quite challenging to design such a system. But just to give some glances, so here is a professional motion capture laboratory using external equipment. So it's huge, it has tons of cameras and other sensors, and it looks expensive and actually is as well. And as it turns out that even though we're using external equipment, often in order to get higher performance, we need to put some reflective markers on the person, so get better measurements. So we still have to wear something. And the other approach is kind of a game changer a few years back when Microsoft introduced the Kinect sensor, which basically is a single sensor, a low-cost solution. I'm not sure about the price right now, but probably you can pick up one for a couple of €100. And so here the idea that in addition to this picture on the left, which is in the visible light, we also get this middle picture where each pixel actually, the color represents the distance from the sensor itself. So it's what often people refer as the 3D point cloud of the object. And from this we can easily detach where the human is located, see what are his parameter, if you could say, and then we can somehow estimate the posture of the movement. So that on the right is the actual input for your games and everything that you're doing at home with Kinect. And as you might guess, this approach is not very accurate. So the other thing I talked about is embedded sensors, which is kind of the thing that we might really want to use for these applications, which would be for healthcare or sports, where we want to carry everything around. And the most accurate systems currently are based on these kind of exoskeleton type wearable sensors. Sounds quite futuristic and looks even more so. As you can see here on the left, it's a full body motion capture system. And just to give you some other insights, on the right there's this kind of finger motion capture glove, so you can also capture small movements very precise, but as you can see, it's quite bulky, even though it still works and it is used as a motion capture system because it has good performance. But as you see, it's something you most probably wouldn't want to wear, for example, when going to work or for studies or whatever. And so fortunately, there's other solution which is turning to be kind of the holy grail and the most popular solution, which is inertial motion capture. So here you can see a high performance inertial motion capture system. On the right, the one with wires still looks a bit bulky, but without wires, it's quite clean. And here, where you have the full clothing, you barely can see that there are some attached to the women. And even though this particular is a high-performance motion capture suit, which costs several tens of thousands of euros, this still, as I referenced, is a kind of holy grail, this inertial motion capture approach, because of some technical things which I'll try to explain very fast. So these inertial motion capture systems are based on what often researchers recall as inertial sensor node. So it consists of multiple sensors. One of them usually is acceleration sensor, which you use just like an inclination sensor. So it's just a mass damped in a couple of springs, and when you turn it around, then the gravity acts on it and you can measure the displacement of the mass, and so you can measure the inclination of the sensor. The other one is a magnetic sensor, which is a bit harder to explain, but the basic idea is that if you put current in magnetic field, there are some properties that you can measure and then figure out what the magnetic field was. But basically it acts as a compass, electronic compass. And then there's this third sensor, which actually is used just to enhance the performance of the first two, and it's even more magic kind. I'm not going to try to explain how it really works, but the idea is that we get the angular rate or the speed, how fast something is turning. And so the idea is that if we combine all these data together, then we can get a really nice orientation estimate. And the most interesting thing is that current developments in technology allows us to create these micro-mechanical systems, which allows to put all of this into a tiny chip. And as the production process is very similar to microelectronics, then you can produce them in large quantities for a very cheap price. And the idea is that they can be really small, so if you compare and scale to 1 euro cent, this is approximately comparison in scale. And so just to give you an idea what this orientation measurement means, is this is a sensor node developed in our institute, so you can just capture the orientation of the sensor, and if you attach the sensor to some body part, then you can obtain the orientation of body part, and basically that's all you need to monitor. And as it turns out, as I said, that these sensors are really cheap to produce, and they're already in most of the conventional electronics like smartphones and camcorders and so on. For example, the tilting is sensed with these kind of sensors that could provide the orientation of the display correctly. And now I'm going to switch to my experience, or our experience as I often refer, as I'm part of the research team in the Institute of Electronic and Computer Science. So the idea is that we got introduced to a quite nasty medical condition called scoliosis. And the idea is that during growth period you get really huge deformations on the human back. And the current, in worst cases, the current solution is just to put these hard material braces, which you have to wear up to 23 hours a day, and it's quite challenging to do that, especially for a teenager. And the idea for doctors was that we might, at least at some point, substitute these braces if we could fully measure this posture and have some feedback to the user, what is the correct posture. And as you might feel, then we can't just put a few sensor nodes there. We had to have some kind of sensing material where we obtain the full 3D shape in order to sense these different deformations. And so in our institute we figure out if we can learn how to connect a large number of these cheap sensors together and also process their data in order to obtain the shape of the fabric, then this might be the solution. So we just took a fabric, put a large number of sensors on top of it in like a grid pattern, produced algorithms, and the output looks something like this. So on the left you have this real fabric with embedded sensors, and on the right there is the models. And the interesting part is that we can do it in real time. So you can do the animation, and if for example, you produce some wearable garment out of it, you can monitor instantly all the movements and everything. And so we designed a kind of structure for wearable system where you have these sensors on human, you attach some transmitter, and then you send the data to some processing device, which could be just a smartphone in your pocket. So everything is portable, and you can just carry it around, and everything works fine. And after the processing, you can start to think about what is the current state and maybe give some feedback back to the user, for example, for the same posture monitoring. And here we have compared our sensor fabric to the previously mentioned Kinect sensor. And so if you kind of superimpose them, you can really see that we have done quite a good job in order to determine the posture model of the subject. And so we have produced this kind of posture monitoring vest, which we have also tested in rehabilitation center in Riga, where they're working with patients who are cerebral palsy patients, usually small kids. And this is kind of a tool for them to learn the correct posture while they're doing other exercises. Basing on the same structure, we also produce some a bit more simple device. So here the idea is that for some patients who have really limited movement, they have to train to, for example, just maintain correct head position in order to further use some equipment specially produced for them. But the first step is just to maintain the correct head position. So we took one sensor from our system, attached all the other necessary electronics, and produced like kind of simple application where with the head movements you control this very simple feedback mechanism, which is easily understood by kids, so they can train their head posture. And here you can see some of the real application, how it was really done. And the other application example is one developed together with Emil during his bachelor work. So here again we take the same system architecture, but we apply these orientation sensors to human knee. And so here the idea is that during rehabilitation process after knee injury, it's very essential to monitor the deflection of the knee. You have to train the knee, but you can't force it to overcome some angles. So this kind of monitoring tool allows you to see your performance and just to control yourself. And here I just wanted to highlight that for all these applications, we had to develop also kind of mobile programs. So right now, most of the mobile applications are based on the sensors that are on the phone or just what you input in the phone. But I think that more and more work should be done in order to connect additional sensors to the phone and provide specific applications for that. And regarding the future, it really seems that the wearables are the thing that we will use for biomechanics. First of all, because that's more or less the only solution that allows us to capture human movement during daily activities. And as I wanted to highlight that we're already really willing to do that. For example, the kind of explosion in the market of all kind of fitness trackers is showing that there's a will for humans to understand what's happening with their body. And as I sometimes like to point out that these are kind of really dumb devices, because at best they have one of these sensors that I mentioned on your wrist, and from that they try to estimate basically everything that they're saying in the application, but more or less they have no idea. They can estimate the steps and maybe a bit more. But in order to attach more sensors, there are a couple of challenges to overcome, mainly technical ones. The ones I'm going to point out, I'm sure someone today will point from other fields. But so we had to work on signal processing. For example, this sensor fusion that I mentioned earlier is a major thing, so we can really track these orientations and human movement. We had to miniaturize hardware and provide alternate power sources because carrying around big battery is quite a burden, and if we want a huge processing power that is often required, then we had to maintain that in some kind of balance. And also, of course, there are challenges regarding integration into fabric, because nobody really wants to put these bulky sensors on their wrists and hands or legs. So we have to think about that, and also about some real practical things like waterproofing or mechanical robustness. Because I think in future what we really need is a garment which you can't really distinguish from a normal one, but which is with embedded electronics that really can improve the quality of our life. Thank you.
Thanks a lot. Do you have any questions? Don't be shy. Okay, please.
I would like to ask a question about illustration in the ninth slide. Yeah, illustration on the left with the external equipment sensors. What is the minimal distance that sensors will capture, and how you can improve that?
It really depends on the exact system. For example, if it's the big motion capture laboratory, then the distance can be several meters. If it's the solution, for example, this is I believe, sorry, was here. So on the table there's the sensor, I believe it's some prototype of this sensor, which is something similar to Kinect, and then the distance is really small because it's kind of designed for that. So it's designed to put on the table and to capture just your finger movement. So it largely depends on the actual application and what it's designed for, but usually it's starting from several centimeters up to, I believe, I don't know, 10, 20 meters, definitely not 100 meters.
Okay.
So any other questions? Actually, I have one question. If you search on web, you see a big bunch of platforms who are trying to connect different devices to one big picture to measure some kind of stuff and to give you diagnosis. I think doctors will criticize that, but still there are some. So what do you think about that? Do you see some kind of future of that we use our everyday devices like mobile phone, computers, smartwatches to gather the big picture of our health? What do you think about it, about this idea?
I'm pretty sure that it's more or less the future because we are already seeing that more and more sensors are becoming closer to the human while he's wearing it, so we can capture more data. And the thing that I also pointed out that this sensor fusion is really essential because, for example, if you want to measure heart rate, then and estimate that somebody is having a heart attack, then you have to have also context what the person is doing, because if just the heart rate is rising, you can't really have an alarm because of that, because you don't know, maybe the person is running up the stairs at the exact moment. So the sensor fusion is the thing that would provide us the most amount of data, and the more data we get, the more estimations we can have, I believe.
Okay, just one more question. I think that young doctors, medical specialists are quite shy today, but I know that you are here. So I wanted to ask a question for them, maybe they would be interested in this. Do you have any projects to collaborate with the health specialists? Because I saw you're dealing with the rehabilitation stuff and some kind of related to healthcare. So can you just say something on it?
Yeah, currently we are trying to involve as much medical staff as we can. Of course, we're a technical institute, so our main focus is not medicine, but more development of sensors. As I showed in the pictures, we have strong collaboration with this rehabilitation sensor, Emil, where we give most of our prototypes to test to them. But in general, of course, we would like to involve more medical students and medical workers into our work and be willing to really kind of try out our devices. And of course, I understand that it's quite a commitment, and it asks quite a lot of trust to just take some experimental equipment and somehow start to testing it. But still, I think there's quite a big gap between what actual electronics do and what harm they can provide and what is the perception of society. And in most cases, there's no real harm you can do, and it more is connected with how you can organize the work together in order to get the best results for the testing.
Actually, we have one more question right here. Yeah,
What's been the results of your studies? I mean, if you compare, like, using your sensors for excuse me, for scoliosis, do you find better results than, for example, standard therapies, whether they be exercise or?
Yeah. Currently, we are in beginning of our study, so like a real medical trial where you can prove in medical terms that the results work usually goes like 10 years, 20 years. It's really a long time. That's why a lot of medical things are so kind of especially drugs and everything, that it's quite a big gap from research to market. And right now we're in early stage of testing. In terms of scoliosis, we have kind of a bit given away that, because it's quite hard to convince somebody to test our device when this is real serious medical condition. Our most focus right now is for the cerebral palsy patient, where they from day to day use different kind of training equipment, and the first results are really good. That first of all, the users are kind of interested and they're happy that they have some interactive connectivity going on. We have presented our results at several medical conferences, but usually they're like early studies, so we can't really prove any medical basis right now, but it's in work in progress.
When you say you presented, please tell me that you're taking measures to protect. How do you present? I mean, how much? Because I mean, there's of course there's a risk as you go along here that you lose intellectual property.
Yeah, I mean, this is more the medical results. So, for example, in collaboration with the Rehabilitation Center, we just kind of introduce them to the device, what it can do, and what are the current outputs, and what can be expected in the future based on this.
And just one small observation based on what Emil was saying, just kind of a follow on. I think one of the big futures in all of this, and probably the IT people would know better than me, but that it's in the big data analytics, which is you take your sensors, you store all the stuff in the cloud, make it part of huge ongoing studies, and you have something really big. I hope that you're considering this.
Yeah, that's one of the major benefits from using electronic tools to measure even the same things that doctor can measure in his office. First one is that you can get the data when you're outside the office, which tends to change a lot. And the second is that you can get these kind of big data approaches where all the people are sending their data, and then we can kind of have some nice solutions that we didn't have before.
Okay, so thanks a lot, Atis. I think if you have any other questions, you will meet him during the evening on the demonstration session or networking event. So let's give him a big applause.